which is kind of HTTP, MQTT, speedy, whatnot. And this is where our layer 7 load balancer Proxygen works. For this specific talk, we're only going to focus on IP, TCP, and HTTP, but it's kind of similar for other protocols. OK, so this is an IP header. There's some stuff trimmed out of it. The only things we really care about for both this talk and, again, our load balancers, they only look at source address and destination address. Everything else, we don't care. And again, this is a TCP segment. There's a lot of stuff trimmed out here. There's so much stuff that goes on in the TCP header that we don't care about. Again, we only care about source port and destination port. That's all that matters for our load balancing infrastructure. And that's highlighted in there in red. And then finally, a very, very, very super basic and simple HTTP request. This just gets the home page. This is nothing fancy. So putting it all together, this is what it looks like encapsulated. We have our IP packet with our TCP segment, and then our actual kind of application payload then as well. For the rest of the talk, we will not look at it like this. We will just trivialize it and think about it like this. All you need to know is source and destination, host, address, and port. That's all we care about. OK, so serving user requests. So this is going to talk about load balancers in our data center and how we got from one web server to many, many, many tens of thousands. So we're going to cover dynamic requests. So this is anything that goes to an actual web server. Once a request hits a web server, our web servers are basically thin API layers. There may be tens or hundreds of requests then to other backend systems, like database, newsfeed, messages, kind of all of that thing, ads. We have kind of software load balancing on the back end. We're not really going to talk about that. That's probably another 2 or 3 talks in itself. But as I said, I don't bite. If you're interested, come talk to me afterwards. So this is kind of what we're not going to cover. We're not going to cover what HVM calls out to everything else. We just care about from a user through our load balancing infrastructure to a web server and then back. OK, so this is an idea of what we are currently working with right now. These are all of our online data center locations. We have kind of 6 at the minute. We have one in Prineville, Oregon, one in Altoona, Iowa, one in Forest City, North Carolina, one in Ashburn in Virginia, one in kind of Fort Worth, Texas, which was the most recent one turned up. In Europe, then, we have our one in Luleå, Sweden. We have a second European data center that's almost finished construction. It's not turned up yet, though. It's just outside where I live in Dublin, in a place called Cloughney. And then we have our third EU data center region, also been announced. It's going to be built outside Denmark, outside Copenhagen, in a place called Odense. So let's kind of, this is where we are now. Let's kind of see how we got there. So let's talk about, just how do we do one request with one web server? We're starting off small. This is kind of still Mark in his kind of dorm running Facebook. We only need one web server. So what happens? We make a request to DNS. Again, we're going to assume IPv4 in this. The exact same happens for IPv6, and indeed, almost all of our internal traffic is IPv6. In fact, most of our new clusters, they don't actually have IPv4 addresses at all. So you talk to DNS, you get an address back. Perfect, everyone's happy. And then you hit HHVM, you make this request, and you get your response back. Perfect, everyone's happy. But our web server can't do huge amounts of RPS. Eventually, we are going to hit a bottleneck here. So how do we serve more people? We need to serve 100 times more people. What do we do? How do we get more RPS? And you can probably tell by the title of this talk, but we're going to throw a load balancer in. So this is where our kind of layer 7 load balancer comes in. It's called Proxygen. This, again, is open source. You should check it out. It's like a Swiss Army knife for layer 7. It can be configured as a proxy, reverse proxy, web server, load balancer. It speaks multiple protocols. Check it out. It's amazing. So what we use it for here is we will terminate SSL and TCP connections on Proxygen. It's fairly CPU intensive. Like when you have to decrypt and encrypt all of this information for lots and lots of different requests, that is eating up your CPU, and our web servers are CPU bound. We want that CPU to actually kind of run PHP and process requests. So we add more load balancer, or we add more kind of web servers in the background, and we put Proxygen in front of it. It terminates TCP and SSL. Everyone's happy. But eventually, we're then going to hit kind of, as I said, like Proxygen is going to be CPU bound as well. We need more RPS. What do we do it? Or how do we do it? And again, this is probably not going to come as a surprise to you, given this talk, but we're going to put another load balancer in front of it. So this is where a layer 4 load balancer comes into play. This is Shiv. Shiv doesn't do anything super fancy. It's based around the IPVS kernel module. That's the IP virtual server. This is open source. We contribute kind of upstream fixes and stuff to it when we can. And the beautiful thing about this is it is network bound. There's nothing CPU intensive happening here. If we have a 10 gig interface on this machine, we can get 10 gig of load balancing traffic out of it, which is amazing. And yeah, so what it does, a request will come in, it will be consistently hashed and sent to one of the Proxygen boxes. The consistent hashing is important, but we'll get to exactly why that is important later. So yeah, this works perfect, but eventually you're going to start saturating. You can keep adding kind of web servers and Proxygens as you need, but eventually you're going to hit the bottleneck on Shiv. You're not going to get any more traffic through this interface. So how do we deal with this? And yeah, I'm telling you, it's load balancers all the way down. So this is, I promise, this is the final layer of load balancing inside a cluster. We do ECMP from our actual cluster routers to Shiv. So this is on layer 3. It's equal cost multipath. Just send it to one of them. They all have the same IP address. Send it to one. So we can then horizontally scale this out. If we need more if we need more network capacity, add more Shivs, which talks more Proxygens, which talks more HHVMs. Perfect, excellent. But this is now our cluster. We have low RPS in the HHVMs, medium RPS in the Proxygen. We're network bound in Shiv. What happens though when one cluster isn't enough? We need to start adding more clusters. So very quickly, I will just give you an overview of the kind of ratios we're talking about in a front-end cluster. We have different types of clusters, but that's not important. We'll have, in a regular cluster, about maybe 10 Shiv instances. This will then talk to around 100 Proxygen instances, and then this will talk to thousands of web servers. No, I mean thousands. I could probably put another 10 slides of web servers in to try and give you the actual scale. So we just add another cluster, and this is perfect. Everything works bueno. But what happens if we want, say, more redundancy, or we need even more capacity? We're talking about adding new data center then. So what do we do? So this is our current setup. We have one data center with multiple clusters. You get an IP, you hit DNS, you get an IP address for this data center. Everything works happy. When we add a new cluster, you can hit DNS and you'll get an address for one or more of you'll get an address for one of the data centers. We'll talk about how the DNS works, how our DNS load balancing later at the end. But yeah, this is essentially how it works. I will say now that all of our diagrams so far have kind of shown a hierarchical kind of architecture, and this really isn't true. We don't have our Proxygen boxes don't have thousands of ports that connect to web servers. So we have our own kind of service orchestration tool. It's like Kubernetes or Mesos, and we call it Tupperware. We write a spec for just say Proxygen or Shiv or HHVM, and we tell it like, run this somewhere in the cluster. I don't care where it is. I just need a machine with these resources, whatnot. So a lot of the time you will have these services co-located in the same rack, and they will talk through the same regular top of rack and kind of fabric switches or cluster switches, whatever. So yeah, as I said, this is important. We don't have like custom hardware with thousands of ports connecting to web servers. That just doesn't happen. Okay, so now let's go into a little bit more detail about how our actual L4, L7 load balancing works together. So let's go back in time a little bit to where we saw this slide. This is the basic architecture. We have ECMP to get to Shiv. Then we have the consistent hashing to get to Proxygen, and Proxygen forwards to web service. And let's bring us back to the OSI model. So we have Proxygen working at layer 7, and we have, and that's just actually proxy requests to an actual web server. Shiv on layer 4, all it's doing is routing TCP sessions to the correct Proxygen instance. And kind of on like layer 3, we have ECMP. It's just sending the request to a Shiv instance. It doesn't really matter which, because as I said, we're not terminating SSL or TCP on a Shiv. It's just passing it through, so it doesn't really matter. So, okay, how does this work? Again, we're going to show it as a hierarchy, but we know now this isn't actually how it works. So, our Shiv instances announce or peer with the kind of top of rack switch over BGP. So all of them run exabgp and announce the actual destination address to /32 to the router. What happens then is a request will come into our layer 4 load balancer. It will do the consistent hash based on the source and destination port and address. And it will kind of hash specifically always to one specific proxy instance. And that's good because then all of your TCP and SSL termination will be done there. You don't have to reestablish a new connection if you do another request because it's already set up there. So Shiv, as I say, it'll do the kind of the consistent hashing. It will also maintain a state table, so it doesn't have to do it every single time. And this is going to be important now in a second, and I'll show you why. So let's actually go through an example. So Puppy here makes a request to www.facebook.com. They will kind of go through our routers. It'll be ECMP'd, and it'll go to a Shiv instance. Again, it doesn't really matter which. It will do a consistent hash and figure out that, OK, Puppy needs to go to proxygen A. And its request is served, and everyone's happy. The cat, on the other hand, comes in. It's ECMP'd to a different Shiv, and then it's hashed to a different proxygen instance. And the state table in both cases is updated. So what happens if we lose one of our layer 4 load balancers? Okay, so in this case, we have just lost one, and Puppy is going to make a second request. It's going to be ECMP'd to a different Shiv instance. But because all of them have the exact same view of the proxygens beneath it, and it uses the same hashing algorithm, it will be hashed to the exact same machine. A thing will be added, an entry in the state table will be added for A, for Puppy, and it will be sent to the exact same proxygen where its kind of TCP session is still active. Perfect, everyone's happy, kind of absolutely no negative effects to the actual user. What happens, though, if we lose a layer 7 load balancer, though? This is slightly different. In this case, Puppy, again, will make another request. We'll hit our layer 4 load balancer. It would normally be destined for A, but A doesn't exist anymore. It's being removed from the pool. It's down something. So it will get moved to a different one. It's not necessarily always the exact next one, but it'll go to something else. And an entry will be updated in the state table for B. It will go to the other proxygen, and its request will be served. Now, what happens if load balancer A comes back online? Say we just was restarted. It was updating its configuration, whatever. What happens if it makes another request? So again, we'll come in, we will talk to Shiv, and now, as I said, normally this would be destined for proxygen A. The consistent hashing algorithm will tell it to go to proxygen A, but our state table overrides this. And this is kind of important because right now we have an active session in B and our session in A is gone. So if we sent them to A, we'd have to reestablish everything again, and that kind of slows everything down. So we will just take what we've said in the state table and route it to B. Another thing to mention here that we do that I didn't talk about before is direct server return. And this is important specifically for static content, not as much for dynamic requests, but definitely for static content. So our layer 4 load balancers don't just forward on a packet to proxygen. It actually does IP and IP encapsulation. So it will get the actual raw IP packet from whatever, Puppy in this case, and we'll put it in another IP packet destined for proxygen. Proxygen will get this. It supports IP and IP encapsulation. We'll take the original packet out, drop it back on the network, and then process the request and return. The reason for this is, as I said, so our layer 4 load balancers are network bound, and our responses tend to be much larger than our requests. So if we sent everything back through the L4LB, we're kind of killing our own capacity. So the layer 4 load balancer is only useful on the way in. On the way out, it goes directly from proxygen routed to whatever user is. This is kind of a representation of it is. So remember, we said this is the representation of a request we were going to use. So this is how it comes into Shiv. We then wrap it up in another IP packet and send it out our interface to proxygen. So this is kind of a better example. Puppy makes the request. This is it. doesn't get modified until it hits the layer 4 load balancer. Layer 4 load balancer will do its its hashing, figure out which proxy it needs to go to, and then puts this IP packet inside another IP packet and sends it on to Proxygen. Proxygen supports IP and IP encapsulation. It takes this packet out, drops it back on the network. All of our Proxygen machines listen on this 1, 2, 3, 4, whatever, listen on this address on the loopback interface. So it will get this, process the request, and send it back out. And again, everyone's happy. So we now know this is how our kind of routing works, or this is how our load balancing works inside the data center. Let's talk about edge pops and how we use them to reduce latency to the actual end user. So this is an image put together by our traffic team back in, I think, 2011. And this is the round trip time to Facebook from different parts of the world. This was when we only had US data centers. Our kind of edge pop infrastructure wasn't really that good. And yeah, you can tell latency pretty much everywhere outside the US is bad. Now, 800 milliseconds doesn't seem like a lot, but you have to remember that you'll need more than one request to load a web page. So 800 milliseconds, while sounding not that bad, could actually be maddening considering you have to do so many round trips. And Facebook is a worldwide company. Most of our users do not live in North America, so this is not good. We needed to do better. So this is going to give you an example of exactly why we did this and exactly kind of what the benefit can be. So in this example, we have a bunny in Seoul who wants to interact with Facebook. Yeah, they're all animals. It's OK. Who wants to interact with something on Facebook.com. For this example, we're going to say they're going to get routed to our Prineville, Oregon data center, which it probably would be. So the round trip time, the TCP connect time is about 150 milliseconds. So it's about 75 milliseconds each time you have to cross the Pacific there. So this is what happens. So our TCP handshake is 3 ways. So by the time we can actually do anything useful with this connection, we can actually send the request in the final ACK. So it's 150 milliseconds before we can do actually anything with this connection. But we use kind of SSL everywhere, so we need to then do an SSL handshake, which is a 5-way handshake. So by the time, again, we can actually make our request, 450 milliseconds have elapsed. We then go and make our request, and it's 600 milliseconds by the time we actually get a response. And this is assuming best case scenario, only speed of light, 0 processing delay, and any of the routers along the way, and our web server taking like 0 milliseconds to process this. This is obviously not going to happen, and it is going to be worse. But this is kind of an example of how bad things can be. So how do we go about making this better? In this example, if we had a POP or point of presence in Tokyo, what would the difference be? So Tokyo to Seoul is about 15 milliseconds speed of light. So how does this make a difference? So we still have to do the 3- and 5-way handshake for TCP and SSL. But because we're only 15 milliseconds away from our POP, this only takes about 90 milliseconds. We still then need to make our actual request that has to hit an actual web server in an actual data center, which is on the other side of the Pacific. But since we have kind of a pool of connections open from the POPs to our origin data centers, there's no kind of setup time there needed, and we can just proxy it straight through back to origin and then back. So we've reduced the kind of round trip time for this request from kind of 600 milliseconds originally, which was not great, and we've cut that down to 240 milliseconds. So that's less than half, very fast. Bunny's very happy. Great news. So let's talk about the load balancers in POPs. How do they work? So we went over of how everything works inside the data center. And kind of things are slightly different in the POP. You hit pretty much all of the same stuff, but we don't have user data in POPs. We don't have web servers in POPs. So what happens is we have a puppy, say, in Germany, going to a POP in Germany, hits a router, gets ECMP'd to a shiv box. It gets consistently hashed to a layer 7 load balancer or Proxygen. But instead then of forwarding it to HHVM, we don't do that. We forward it straight back to an origin POP, a data center. And then this will do the same process as we just went through. It will go ECMP to a shiv in the data center, to a Proxygen in the data center, and then finally to a HHVM and back. So let's talk about our DNS load balancing. So we know now kind of how it works inside the data center. We know how it works inside the POP, but how do we know which POP to send people to? That is the next challenge. So we do this with a system called Cartographer. There are many different kind of factors we need to consider when we do our routing. First is closeness. So how close is a person to our POP? And this is closest from a network latency point of view, which, believe me, isn't always the same as physical closeness. There is some weird routing decisions happening on the internet. So you might find that, you have a POP in a city very close by, but a POP in a city further away is actually where you're routed to and you have better experience with because of how your packets are getting routed. We also have to factor in capacity. So this is a kind of capacity of our POPs. Do we have enough backbone capacity from our POPs to our data center? Are we overloading our transit or peering links inside the POP? Are we running out of CPU and Proxygen boxes in the POP as well? So we have to factor all of this in and then kind of create a map of where to send everyone to. So how do we measure closeness? We do this with a system called Sonar. So what we do is, for a very small percentage of CDN requests, so this is like images and stuff, I think it's kind of traditionally profile photos that they do this with. But instead of sending it to the POP location we think is the best performing, we will purposely send it somewhere else, to someone further away or somewhere we think that's going to be worse performance, and then we'll kind of measure the round trip time. And we do this for a very, very, very small number of requests. But we have so many people using Facebook, issuing so many requests, we can build up a fairly accurate map of how close certain net blocks are to certain POPs. And we use this in our kind of decision making then. So this is kind of basic cartographer architecture. So it will look at capacities, and this can be different types of capacity, as I said, like into the POP, from a POP to our data centers, or any other servers inside the POP. It will check out this latency map of how close resolvers are to Facebook. It will look at any routing problems, like is there a fiber cut somewhere? Has a shark attacked a subsea cable again? That's at least twice I've seen that in my career now. It's crazy, but it happens. And then like health, do we have other kind of problems with our POPs? Are they on fire or something? So Cartographer does some offline processing every about 5 minutes, takes in all these details and creates a map which it pushes into TinyDNS. TinyDNS runs all of our DNS infrastructure at Facebook. And yeah, this will then create a map of, okay, so ISP in country A, you should be routed to POP A normally. But if we suddenly run out of capacity, it's like, okay, we would route you to POP A, but we'll route you to POP B now. And this happens all the time, and we use it to kind of keep capacity fairly stable and level. So here is maybe a slightly better kind of diagram of its architecture. So this is all inside Facebook's infrastructure. And then we have kind of ISP resolvers. We rely on, like most Facebook users use their ISP's resolver. If you're using like Google DNS or something, I mean, that's kind of your own fault. We're not as easy to target people that way, but we have other means. So this is an example of Cartographer in action. So the kind of light green line going across is our actual capacity limit. This is what we think our max RPS is based on our traffic and CPU capacity and whatnot inside this POP. And this orange line here is actually the user demands. This would be the traffic we would send to this POP if Cartographer did nothing. And obviously, we would try and send much more traffic to it than we can actually handle. And this little squiggly green line here is Cartographer working to keep our traffic in this POP as close to our max as possible. And you can see here, it actually does a pretty good job at it. We don't overload any POPs. All of this traffic then we would send somewhere else close by that has capacity, and then we would do the reverse kind of if we have excess capacity here. Here's kind of an example that might be slightly easier to understand. This would be a lot of POPs in a region. You can very clearly see they all have slightly different kind of capacity limits. They might have different kind of generations of hardware. They might have different kind of links coming in. And you can see it all tries to keep it very, 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 very close and stable. And it's generally very good at this. And then you can also see the offset time zones that work. So this would be a bunch of POPs, say in the US or in Europe, are all kind of very close together. Here's an example then of our global load shedding. So this cartographer is working 24 hours a day, 7 days a week, constantly moving traffic around from place to place based on issues. You can see it kind of moves a lot of traffic. There may have been some serious events. We may have had a fiber cut, may have been something big, and we have to automatically move a lot of traffic to somewhere else. We never generally have to move traffic manually or anything anymore. I remember back in the dark ages, I've actually had to, type into a config file and move traffic from one part of the world to another, but that doesn't happen anymore. This all happens while we sleep. We have automatons taking care of all that for us. As I said before, we don't like doing things for the sake of doing things, or we try to automate as much as we can because, as I said, we've had to because we've grown so fast. We don't have the amount of people to do all of this stuff manually. So I want to talk a little bit about monitoring. So monitoring is kind of my passion and what my team mostly focuses on in Dublin. I'm afraid we don't have enough time to talk about monitoring, though. I will very briefly touch on a couple of things we look at, though. So we actively probe all of our POPs from all of our other POPs. And we'll have collection agents that will do real-time monitoring of our actual traffic levels, our requests per second and whatnot. We have agents outside of our network that will probe our POPs and make sure everything's healthy. And as well as that, we monitor a lot of fairly high-level metrics that we think directly correlates to per-user experience. So we will kind of monitor client latency, because that's kind of a big deal. We'll monitor retransmits, error rate, are we serving a lot of 500s or 503s, or what's going on here. It will do retransmit percentage, and also total egress. So I showed you the weekly pattern of our traffic. If we suddenly lose a few terabits, that's definitely a problem. Something's probably gone wrong here, and someone has to look at it. So yeah, if we notice, like I said before, if we notice that one of our POPs is unhealthy, we don't actually do anything anymore. Our automation will automatically figure this out and move traffic to somewhere else. We might make user experience slightly kind of worse for a short period, but I think service degradation is better than no service at all. So if we didn't drain the POP, people would be trying to hit this POP that's down, get 404s, get nothing. We can automatically drain it and say, no, okay, I mightn't be sending you to the best possible location, but I'm sending you somewhere and it will work for you. So let me talk a little bit about open source. So this talk wasn't all about us showing off, look at all our cool toys. It's about anyone can build a very, very similar system. Pretty much all of the components we use are open source. Either we used some open source tools to build it, or we built it ourselves and then went and open sourced it ourselves. So Proxygen it's in my top 2 favorite open source projects at Facebook. It's truly, go check it out. It's absolutely amazing. It does all of our layer 7 load balancing everywhere, and various other bits and pieces as well. It's really, really great. TinyDNS runs all of our DNS infrastructure, and it's worth looking up. IPVS is the IP virtual server. So this is the kernel module that Shiv, that our layer 4 load balancer wraps. Shiv is kind of a thin wrapper. It does some health checking. It talks to our service management stuff. But IPVS does all of the heavy lifting. It's open source. You can go check it out, download it yourself. ExaBGP is the BGP daemon we use in Shiv. We use it in a few other places as well. It's very, very scriptable, which is why we use it. And we generally only use super, super, super basic features. So that's very, very useful for us. Python gets a message here because it is the glue that holds pretty much all of Facebook infrastructure together. A lot of our monitoring tools are running in it. A lot of our automation tools are running in it. Pretty much all of our mediations are written in it. We use it very, very heavily at Facebook. We love it. I love it. I did also mention HHVM, which is our web server. It is also publicly available to kind of anyone. Go check it out. It's also powering a lot of the largest websites in the world, so it's not all bad. Okay, so let's do a very quick recap for those of you who weren't listening or just don't care. Edge POPs. Edge POPs are important. We can use it to just putting servers closer to the user can really, really, really make a massive difference. And I said we have no web servers in the POPs. We have no user data in the POPs. All we're doing is terminating kind of SSL and TCP layer. And this is the problem. It's the round trip time that's the killer. So just by moving, or just by putting some servers, and not even a large amount of servers, close to the user, we've more than halved the time needed to make a request. We do direct server return. This helps us kind of ease the load on our layer 4 load balancers. And we use kind of 3 basic load balancers: our DNS one, which is based on Cartographer, our TCP one, which is Shiv, based on IPVS, and our layer 7, which kind of HTTP, speedy, MQTT, whatever, is Proxygen. And I think that's pretty much me. It was a little bit faster than I thought, but if anyone would like to ask me any questions, I'm more than happy to answer them for you.
Guys, we'll use the mic for the questions so that I can be on the video as well. Anyone?
There. The usual stupid question. You were saying Python. What version of Python are you using?
So, so we have a couple of different versions of Facebook. My team, we only use Python. We only use Python 3 since at least about a year. Right now, our current version we're using is 3.6. Our build tools, you can target really whatever you want. Our current guidelines are it should be Python 3 unless you have a very, 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 very good reason for it not to be Python 3. And the only really good reason for that is I really, really, really need this library, and it's not available. But yeah, pretty much all of our code is Python 3 now. I don't know a lot that's still Python 2 or 2.7. I know certainly my team. Some. My team anyway, I know last I checked, I think 20% of the Python 3 at Facebook was kind of our team. But it's being pushed. We love Python 3. Async I/O is the best thing since sliced bread. That's all I can say. Yeah. Does that answer your question?
Yeah, very, very much so. And you were mentioning async I/O. So how are you leveraging all that, and what's your experience with it?
I like async I/O. So as I said, I mostly work on network monitoring tools, and that's generally what I do. We converted, or the tool that I've been working on mostly for the past year is all async I/O now since about a month. The last bits of it were converted over about a month ago. I like it. We halved our memory usage at least, and we can get way more requests through. So it's great for us. We're doing way more requests with the same amount of hardware, so I really can't complain about anything. Yeah, it's good for us.
Hello. I don't know if it's working. Okay. God, you killed me because you didn't talk about monitoring. I have a couple of questions. When you were talking about the issues when the different layers, load balancers fail,
yep.
In the second example that layer 7 load balancer was down.
Yeah.
I'm curious, how does the layer 4 load balancer know that, in the example, layer 7 load balancer A is down? Do they have like a heartbeat kind of protocol between them, or does the layer 4 load balancer knows when someone is just asking to go to layer 7 load balancer A?
Yep. So our layer 4 load balancer Shiv, we'll do active health checks of all of the proxy machines below it, and it will actually mark them down if it realizes this isn't healthy. We have our kind of like our service management tool. It will be marked down that this is okay. This is unhealthy. Don't send any more traffic to us. It's pushed out to all of our machines. It's based on like Zookeeper. So it's pushed out very, very quickly. And yeah, it'll actively monitor it. It notices if it's down, don't send any more requests. All of the layer 4 load balancers have the same view, so that none of them will start sending traffic to it anymore. Does that kind of answer your question?
Yes. Yes, thank you. And the second one, it was about the monitoring, because you said you were monitoring the different POPs,
Mm-hmm.
and when you found out that one is unhealthy,
yeah.
what do you do? Because you're saying that everything moves automatically, so you don't really do nothing actively, or?
So yeah, we generally don't, like, it will be drained automatically. Like, someone will be paged and know that, hey, something really bad just happened here, and someone probably wants to look into it. But the kind of remediation happens automatically. We'll probably want to know, why did this go down? Do we have a fiber cut? Like, can we get this fixed quickly? But the actual kind of straightaway remediation, like, let's allow these people to use Facebook again, that's automatically taken care of. Like, we don't manually have to do that anymore. We don't wait until to see if it's bad. If we know it's down, a lot of people can't get to Facebook, we've lost a lot of traffic, it'll automatically move it away.
Okay, thank you.
So this is based on DNS, so Cartographer will make this change.
Hi James, thanks for the talk. I just wanted to ask, because a couple of years ago at a conference, I remember that I heard that Facebook synced their DNS configuration via BitTorrent, something like that. I don't know if it's for Cartographer.
Yeah.
Is it really working?
I'm not 100% I'll have to double check this. If you come to me later, I don't want to give you an obviously false answer. I'm not 100% sure. So we do use BitTorrent for kind of distribution of a lot of things. Like when we do deployments, it's all done over BitTorrent. When we're distributing packages, it's all done over BitTorrent. We contribute to the BitTorrent tracker that we use. It's written in Go. Pretty much all of the conversions to make it IPv6 were done by Facebook. And we use it because it means that 90% of the traffic is within the rack, and it's super fast and awesome for us. A lot of our configuration, though, is done by Zookeeper. So I'm not 100%. Which I'd imagine is I will answer this after. I think it's probably Zookeeper is how most of our configurations are pushed out. But I'll double check. We do use BitTorrent heavily for our packages and kind of deployment infrastructure.
Thank you.
Last question, guys? Anyone? Okay, thank you, James.
Thank you.